Let's talk about clothes. Everybody has them, and we put them on every day. To keep it interesting, we always try to wear something different, or else it would just be boring. So how many ways can we wear our clothes? Well, let's figure it out. Let's say, for example, I have 3 pants, and let's say 4 shirts. Well, then how many different outfits can I wear? Okay, so if I put on a pair of pants, it means that for every different shirt I wear, I have a different outfit. And every time I change my pants, I can wear each shirt again as a new outfit. Using math notation, we can describe this as 3 times 4, which is 12. Let's say now I have 2 different pairs of shoes to wear, too. For each pair of shoes I put on, I have a whole new outfit. Since I have 2 pairs of shoes, I can say I have twice as many outfits. This can go on for as long as it needs to, depending on how many elements of your outfit there are. By multiplying out all the possibilities like this, we're using something called the counting principle. As a general definition, the counting principle is this. When there are m ways of doing one thing and n ways of doing another, there are m times n ways of doing both. This is true for pants and shirts, cars and brands, hats and colors, and everything else that has some kind of variety. What if I had, for example, 4 shirts, 4 pants, 4 shoes, and so on? Well, by using the counting principle, we know that I'll have 4 times 4 times 4 and so on different outfits to wear. Or if I have a lock, which has different slots, and in each slot I can choose one of 10 numbers. Then that means the total number of possible solutions is 10 times 10 times 10 and so on, depending on the number of slots. If we have 10 different numbers to choose from, and let's say 5 slots, then we have 10 times 10 times 10 times 10 times 10, which is 100,000 different solutions to that lock. We can use a shortcut to write this, 10 to the 5th. But let's say there's 6 slots. Well, then it's just 10 to the 6th. But what if there's 12 numbers to choose from? Then it's 12 to the 6th. To be able to put in any number we want, we can write this as a formula with variables. N is the number of things to choose from, and R is how many times you can choose. This is called a permutation, specifically a permutation with repetition. It has repetition because, like in the lock example, we're able to choose the same number more than once. But what if, once we choose a number, we can't do it again? This is like drawing cards out of a deck. Once you draw a card and put it somewhere else, you can't draw it again. This is a permutation without repetition. Thinking about this mathematically, it's very similar to permutations with repetition. When we have repetition, we multiply out the number of choices we can make like this, n times n times n times n. But if we're not able to repeat, then every time we make a new choice, we have one less option because we picked it the previous time. N times n minus 1 times n minus 2 times n minus 3, all the way until we hit 1. To write this quickly, we can just say n factorial, which means the same thing. But wait, there's a problem. I'll explain using an example. Let's say we're making a computer password using the 26 letters of the alphabet, but once we pick a letter, we can't use it again, and we want it to be 4 spaces long. Well, for the first space, we have 26 choices, one for every single letter. For the second space, we have 25 choices, because we already chose one in the first space. In the third space, we have 24 choices, and 23 choices in the fourth space. So I do 26 factorial, right? Not exactly. This is the problem. If we do 26 factorial, it'll multiply every number between 1 and 26. But we only want the first 4 numbers, 26, 25, 24, and 23, since our password is only 4 spaces long. So how do we get rid of the rest of these factors? We divide them out. But what do we divide by? Well, let's see. We have 26 factorial on the top. If we divide every factor we don't want by itself, which is always equal to 1, then we're left with the numbers we do want. Let's see, the 22 cancels out, the 21 cancels out, the 20 cancels out, all the way to the end. As you can see, we've created a factorial on the bottom now, 22 factorial. But where did that come from? Well, if you get the number of different choices, in this case it was 26, minus the number of slots or spaces, which was 4, then you get the number to factorial and divide by, 22. This works for any numbers. So, instead of just 26 factorial, it's 26 factorial over 26 minus 4 factorial. And don't forget the parentheses. This means there are 358,800 different ways to make our password. The formula for this is n factorial over n minus r factorial, where n is the number of things to choose from and r is how many times we can choose, just as we established. Since mathematicians are lazy and don't like to write as much, they made a new kind of notation just for permutations. It looks like this: a normal-sized capital P with two smaller numbers besides it. The one on the left always represents n, and the one on the right always represents r. When you see this, you solve everything just the same. It just tells you the information you need. Okay, so far we've covered the counting principle, permutations with repetition, and permutations without repetition. So let's go over combinations without repetition. Before we start, I have to make something clear. Permutations are different from combinations by this simple rule. Permutations are different with each order of choices, and combinations are the same no matter the order. For example, let's say balls labeled 1, 2, and 3 are chosen in random order. The possibility of picking 3, 2, 1 is a different permutation than 2, 3, 1, but still the same combination. Since each combination includes multiple permutations, we're going to have fewer combinations of balls than permutations of balls. In fact, there's only one combination of balls to pick in this example, but there's 6 permutations. Where did the 6 come from? Well, we started with 3 balls. If you take 3 factorial, you get 6. This works for any example. There's always r, the number of times we choose, or slots, factorial, more ways to make permutations than combinations. So if we divide the number of ways to make a permutation of something by r factorial, then we get the number of ways to make combinations of it. And that's our formula for combinations without repetition. Just divide by r factorial. As for notation, it's the same as before, only with a capital C instead of a P. And that's really all there is to it. See you later.